to the calibration in hydrology. That was the title that organizers proposed, and I was thinking in perhaps put a subtitle. What I'm going to talk today is parameter estimation from the point of the statistical analysis and some examples in verification. That's what we have been doing. We are trying to do this in the whole pan-EU, and for us and for the whole community, what we have been talking the whole day here and perhaps the days before is, and the grand challenge that we have in our community is how to develop an ability to global monitor and predict the movement of water at landscapes less than 4 kilometers. We are doing an enormous amount of effort with satellites and with remote sensing and with stations like this one. And the big problem to address this thing is if we want to predict globally, then we have to have models that should be tested. And this test should be across locations and scales. If we just calibrate a model at some point, that's not enough to say this model is working relatively well. So the models, as you see here, if you assume or estimate parameters in one place, you should do what Clemens said at some time ago. You have to test it somewhere else in different locations, perhaps ungauge or proxy basis, and even more, you should do it across scales because we have lots to do with the scaling, because most of the observations do not come at the same scale. So we need to talk about a holistic framework if we want to address landscapes and large-scale modeling. We have too many cells, there are too many parameters. Even the simplest LAMP model will tend to be over-parameterized if you go over a million of cells. You have to regularize this. You cannot let simply parameters flow around and this is just the result of an optimization algorithm. We have to talk about how to transfer and how to validate. We have to find out with methods whether we could identify these parameters given the data. If the data is not helping you to identify the parameters, then we have to start making observations for doing that. We have to combine what is the uncertainty of the model, what's the uncertainty of the data, and we should clearly expose the user to this information. If we want to do predictions in large scale, we also have to improve computational efficiency, and finally, we have to verify our models. The way we are addressing this is simply devising 3 big blocks. One is the multiscale parameter regionalization I'm going to talk to you. The second part is how to estimate these parameters and how to infer them, and perhaps the third part is how to verify in a nested approach because the measurements are done at point scale or with a big sample size or like grays at almost 1 degree. So we have to address the scales in our evaluation. Let's go for the first one. In hydrology and land surface modeling, we have already addressed this problem. We already know the physics. We could address in the main fluxes. We are in that position. We could write nice, beautiful equations. And we did so. We developed a model which is based on actual knowledge. It's basically a framework where we can put all the knowledge we have in the community. We want to have information of the states in a given cell. We have forcings which are coming at a different scale, let's say the scale L2. But the difference of this model, which is basically the same as the ones you have been talking about, is the presence of the subgrid variability. If we want to infer something at some point, we need to have a support information. If we want to have porosity of the soil, we have to have the soil types in the lower scale so that we could infer porosity and make this evaluation consistent with the data we have. We cannot simply calibrate parameters, LAMP parameters like in HVB, which is called field capacity. This parameter cannot be linked, and if it's not linked to the physics of the soil, we cannot transfer. Okay. So that's what we put in our model. The model was developed in the principle that we need to experiment with these possibilities to transfer. Actual models do not offer this, and so we rewrote and we make a model that is free, it's open source. You can have a look at everything we have been doing, and you can even get the data if you request it. All models we have been presented in this workshop can be basically written down in these equations. You have state variables which change over time. They are located at some point in space and time. And you know all that. You have structural errors, you have observational errors. The holy grail of the whole thing is how you find these effective parameters that you put into your model. And these parameters are local specific. They depend to the cell I. They are here specific, and sometimes are time specific. For example, porosity of the soil. If the land cover is changing, the porosity would also evolve over time. It even change over time of the year. It's not constant because the organic matter is changing. So you have to take into account this if you want to do a good prediction somewhere else. We have been addressing this by just fixing up objective functions like this. We make very complicated things, and we are trying to infer basically these effective parameters. But the question for us was, but that is probably not the way to go. We should take into account the subgrid variability. In other words, what is behind the porosity? What is lying there? And we have beautiful maps at the moment. The United States has, for example, Surovo maps of almost, they say, less than 100 meters resolution. In Europe, we can get information, and even across the globe, we can get the whole harmonized soil map at 1 kilometer. So we could infer perhaps for 4 kilometers, this decent parameter. In hydrology, you will have plenty of papers, and here's just a simple sample of how people have been trying to address this problem of parameterization. Just a simple summary for you so that you could follow what I'm talking about. The first one I heard about was Ripley, USGS, long time ago. He developed a model which was called PRMS. And I was at some point in contact with him, and he guided me to do something like that in order to parameterize PRMS. The basic idea was just to take things from the lower level, aggregate them in some way with GIFs, make classes, classify these classes, and get what he called response units. It works well if the land cover is static. If the land cover is changing over time, your units are not changing. And that was, from the beginning, for me, not useful method because I was trying to assess land cover change. But people repeated this example over years, and we keep repeating now, until others came up and say, no, that probably is not the way. We should not do this thing, because the moment we fix a response unit at some point, and then we calibrate the parameter, we cannot transfer. So these authors here say, no, we should regionalize it. In other words, we should regularize this field so that they don't vary ad hoc and they are fixed to some information. That was the proposal, to fix up some global parameters that can change, and they are not time or space specific, but they link through functions that we know or we assume that they are connected with the parameters we want to have in the model. We said, oh, but here's the problem. You cannot just simply average things in ad hoc way. Some things do not average linearly. You need to know how to upscale every parameter, and that's the work we have to do. So we changed and we proposed this method. We basically move this compartment here to the lower level. So we go and look the information in the best quality we have, infer the parameters at the lowest level, and then try to do the calibration or the data assimilation. So we have two steps. One step is what we call the regionalization or the regularization. So we take fields of physiographic characteristics or land cover, like mu, u, null here, and we have coefficients that have to be assimilated or calibrated. Once we know these fields at this lower level, then we have to find out or infer ways how to average them. We did that, for example, here in the Ohio Basin. It's almost 1.something thousand millions of square kilometers. We got very detailed information of clay, sand, organic matter, and we got functions like the pedo transfer functions for the saturated porosity of every layer, because the soil sample contains layers. So we have to get rid of the field capacities and this stuff, and we just quantify what's the available water in each layer, so that we end up for the 10 centimeter soil with a high quality average value at the 800 meter more or less, assuming some parameters for the transfer that we take from literature. Once we have that, we could infer porosities using algorithms that can scale our harmonic means, for example, which are listed in literature. It's not our invention. soil physicists have been working on that over years. And the idea of this realization says that you should get models that can be scaled up based on this support into different scales, but provided that they reproduce discharge in a decent way. So the error between these two simulations should be less than certain error. We did that, and I show you here the effects of comparing land soil moisture, for example, in a catchment in Germany, compared with the response units and NPR. We took land surface temperature as reference just to have an idea how this thing is giving you whether the model is responding or not. So we are in summer. The highest correlation that land surface temperature has with soil moisture happens in Germany in July. We get a high correlation. So we expect when this map is red, we expect dry soils. And we calibrate the model. We repeat this calibration many, many times. And the nice thing is that both calibrations got almost the same Nash-Shackley event discharge, but the states of the soil moisture were completely different. Because when you optimize with an integral, and you let the optimizer do whatever they want, and you don't constrain, the only thing that matters for this algorithm is to have the right average that generates the discharge. And that's what happened. So the system didn't respond. You got the same discharge, but you got the wrong soil moisture. So if you are doing this in your model and you are simulating, you can imagine the error you introduce. So when even the models was not able to measure something because it was raining, for example, this model react, it went to saturation, here's the fraction. It was completely saturated now because it has the right parameters, because it's the right physics of the soil, whereas the other model had not yet in the saturation because the parameter was fixed according to a response unit which has the wrong parameter. This not only helps you to get the right state, it helps you to minimize the number of parameters enormously. If you take this catchment, which is about 4,000 square kilometers, and you put 20 parameters for each response unit, you end up with 1,040 unknowns that you have to find. With our method, we only have 52 numbers, so we reduce drastically on the number. If we don't do a response unit, then you have lots of unknowns, and this will make your system ill-posed. So once we did that, we started in this little catchment here. We said, okay, but that's not enough. We have to test it somewhere else. Does it make sense? Yes, it makes sense. The red numbers shows you how this model performs in different catchments, which this optimizer never saw before. We got good performances there, with exception of some catchments which are known that have problems with either precipitation or we have infrastructure, or for example here a large dam which changed the response of the catchment, so we cannot really invalidate the model. But we keep testing, and we went to US. We just plot here the same results. The red numbers are plotted here in this map showing runoff coefficient and Nash-Shackley. We were interested to know whether does it work only in humid places or does it work also in semi-arid regions. So we went to US. We took two catchments there. It was relatively simply to do that because the data is available online. We could do this in 3 weeks with colleagues of US, and we test the model. Here's the performance in Germany. We took this gamma parameter, these 52 constants, put the model there, put the data we got from NLDAS, and this is the response we got for 82 catchments in Ohio. We got bad performances somewhere here on the top, but that's because of the soil model. The snow model or model is not good enough for these conditions. We compare also in the Red River in Arkansas, where we found literature of his colleague Liebnet from that time working with Lettenmeyer. And that's the performance that this model got here with the unified land surface model. Our model did much better than that without calibration. And the reason why is because it takes into account the degree variability of the soils and takes into account what has to be transported. Not only that, but the soil moisture compared to other models that have nothing to do, the anomalies, what we were talking about, show a very good similarity with other models and with the observations in a large field test in Illinois. Why it happened? because the gamma parameters I was talking about, not the effective parameters you were talking about, the gamma, these transfer parameters, the regularization parameters, they tend to be quasi-invariant in scales. These are results of all simulations. You can find the reports here. This is the numbers we get with all simulations in all other scales moved to the scale of 8 kilometers. So you have here 3 scales, and each scale contains 200 members, and that's the average we get. And that's what you get when you do response units. So when you calibrate with a given response unit, you do good result at the scale you calibrate, but the moment you use this for a different scale, it performs very badly and could even go in negative. On top of that, you have to take care on how you do the routing. So for the routing, you have to take care on the details of the river network, and for regionalizing, you have to take into account the properties of the real length of the river, the slope, and area in which you have land cover. Not only that, but it helps you to reduce enormously the computational time. So that allows, and here's the proof, if you calibrate at 1 degree in these Ohio catchments, you can save almost 60% of the computational time and get basically the same performance. So now we have these gamma parameters. We reduce the problem of parameterization. This is the parameter space of our model. We have 52 constants to find out. And the question is, which ones can be identified and which ones are important for calibration? Not all are born equal. That's what we know. And there are lots of methods to find out this thing. One method is, for example, the derivative method. Very expensive method. But this method helps you to find out what is the largest flux. So it looks into what parameter changed the derivative of the flux. And it shows here that the most largest parameter here, that's the impact with this method we develop here, is one parameter related with evaporation. And that's true because evaporation is one of the largest flux. But if you do optimization with all parameters, it has nothing to do with this sensitivity analysis. When you do something like the variance-based simulated sensitivity analysis, then you get something similar to what the optimization. For optimization algorithms, these are the parameters that contribute to modify the objective function. So you see something here, but this, of course, is very expensive. Then you would ask why I should do a full Sobol expansion if I can do just optimization. Well, we said because not all parameters are informative. So you have to find a method. And that's what we did with this efficient elementary effects, which is a manipulation of an improvement of a method proposed by Morris and Campo Longo. And it needs only 600 evaluations to tell you, I cannot go into the details, but basically it's just a sampling method that varies every parameter space at a time and finds out a possible path. And then it evaluates which ones have affected most the objective function. And in 600 evaluations, it finds out that all these numbers here have something to do. And if you just take them and optimize, you need only 4,000 model runs to get an optimization function which is almost equal to the one you got with all parameters. So you get a huge computational benefit on top of that with almost no decrement in your objective function. So combining these two methods, regionalization and informative sensitivity analysis, you can gain an insight where you should optimize and what parameters bring you information to your model. Now we have to test it, and one way of verifying this is to go into different scales with the goal and hypothesis that most of what we do as hydrologists is to take discharge as an informative variable and try to infer other variables, state variables that sometimes are hidden or that probably are observed by a satellite. The question is, can do this to estimate uncalibrated water fluxes or states of different scales? Yeah, can we do that? Perhaps it's a necessary condition to put discharge in, but probably it might lead to biases or problems with the states and fluxes. So that's the case. We took this information, it's all open source. We got this, and the first thing we saw is there's a completely unbalanced situation. This is the rain gauge, which is free and was produced by this institute, and it's called EOPS dataset, and it is freely available at 24 kilometers. So that's the thing, that's the product. You see clearly here that some states are providing a lot of information, others not, and that's how it is. We got stream gauges from GRDC and Eurofriend. We get information at latent heat and FluxNet, and we got also fields of latent heat from this product, which is also freely available. And on top of that, we got about 50 realizations of this product, ESA-CCI, which is a composed product from ESA, which contains active and passive microsensors, microwave sensors, and on top of that, we take grays, all of them at different scales. The question here was how good it is, the model, first in Europe. If we just calibrate at every place, the performance of the model at every place is doing relatively well, with the exception of some catchments where there is anthropogenic activities going on, for example, the hooker, in which we don't have naturalized flows. But in general, we can say we can be satisfied with respect to this charge. What happens with respect to the other variables? That would be the question. So we set up this model framework. We have a model that could run simultaneously at different layers, at different scales in a nested approach. So we can run the model and estimate variables at 24 kilometers and estimate fluxes at 96 kilometers because we can scale up the parameters of the model. And we can also estimate fluxes at anchor points and see how good it is. Well, the moment we just sample some of them, that's the problem of sampling, and we take only these basins here across Europe, that's the reduction in performance that you get. Because the algorithm is getting less information, is less informative, and what you see here is still remains suitable in some places, but in other places, since there was not information of this place, the optimization algorithm moves away some parameters so that the performance is not good enough. Still, the model is producing relatively good results for most of the basins. The conclusion effect here was that what was affecting performance is basically area. Those catchments which have middle size and have anthropogenic activities going on, heavily dammed or has been restricted, have problems. And the next factor which influenced very much the performance is the rain gauge. So small catchments with very few gauges, rain gauges, have a very bad performance. Compared against grays, we were surprised to see very good correlations between the anomalies that the grays produce, the total water storage. So what we did is in our model, we calculate the whole amount of water which is stored and calculate the anomaly in the same way that grays is estimated. And we found out a very good agreement with all the simulations that we had in our little model. And here is the catchments we use for the verification. At some points, we, of course, don't get the extremes that we were expecting, and we are trying to assess why it's not happening. How is the performance in locations like the anchor points? We found good agreements in forest sites, with this, for example, in Germany, but we are getting troubles on these locations in grassland and shrubland, especially in semi-arid regions. So that means that this information, if we assimilate with this framework, it will bring some information to the model because this was not there when we optimized. We need more information. Compared with the soil moisture, we were a little bit disappointed because first of all, the product is a composed. We didn't get information of the depth of the composed product, so we could not really guess what they are providing. On top of that, we got lots of missing values, so the standardized anomalies are biased. And the worst of the cases was that this composed product didn't show, for example, extreme events like 2005 in the peninsula, Iberican Peninsula. So we see here it's just a wet bias, when in fact the EOPS information is telling that you are in a dry situation. As a summary, we plot in a Taylor diagram all these results. So you here see in this axis the correlation. A perfect model should be here, and that in these contour lines here you see the root mean square error, and that is the ratio of the standard deviation of the observation compared to the model. And what you see here is that, first of all, the sample size for assimilating these charges is probably not good enough for the arid regions. Here the red and the blue is telling you places which are humid. So here's energy limited, the red ones, and humid places with blue. And you clearly see this when you change that. So arid places in Europe have big problems in summer. We go here. In winter, of course, evapotranspiration is not a big trouble. That's why the product is doing very well with the model. But the moment we go to summer, we have troubles. The model here, the comparison reference values we have are not able to catch the standard deviation, and we have, although a good relation, we still have error. With respect to the soil moisture, that's one of the most affected variables. We have here problems, for example, for the energy limited areas, water limited areas, and for the humid regions here, it's relatively well in summer, in winter. For the total water storage, it's basically the performance swapping over the period of winter and summer, and in generally the correlations are between 0.6 and 0.9. So that tells us there are potentials here to use this data, different scales, and use them, combine it in this framework to assimilate the information we have seen in different satellites. So we have shown you an effective method that takes into account regionalization or regularization of parameters for a conceptual model. It's possible to transfer these parameters across scales, and you could have methods that help you to identify which parameters are informative instead of just calibrating all of them. That's the best approach. Not all variables have to be used at some point in time. If you are optimizing snow, then it makes no sense to do this information. There's no parameters in summer. You need to know only winters, things like this. But when you mix up everything, then there are some parameters which dominate, and they will never be optimized or can never be calibrated. So the multiscale regionalization method works well and allows you to transfer across about 300 basins, so it's a good sample. And with this, we could say and conclude that there are good signals. For example, the discharge is a fantastic integral. The grade signal could help you to find out a whole anomaly, and the evapotranspiration that is based on reanalysis could guide a model like this one to get the states right. And if you, on top of that, put anchor points in your model, and you really take care of what's happening in the ecovariance stations, you could infer parameters that are needed for grassland and forest and for other kinds of land cover. And with that, probably I close my talk, and thank you for your attention.
We had a question earlier about the fact that could decrease the number of parameters to calibrate the model.
Yeah.
According to your approach, do you have a limit of number of parameters, minimum or even also a maximum limit of number of parameters? How dependent you are of the model, the hydrological model?
So the way we did it, and we are doing at the moment, is we take a new model at the moment. So we've got some information how it works. So we found out, for example, if you want to get this charge right, you have to do well in soil moisture parameters. That's one of the most sensitive ones. So you have to regionalize. This is the first one. Possibly all models give you this idea. You should be guided by a sensitivity analysis to do this, because if you take a land surface model like NOAA, this model has at least 10 times more parameters than I have in this conceptualized model. So you cannot regionalize in the first moment everything, because you don't know how. I mean, you have to start with this. if you have a bunch of 20 parameters that you regionalize, like we have at the moment, you would see what benefits that brings to you. This process was trial and error, and it took a long time, but once you have some experience, you find out that some things will repeat. Soil moisture will be important because that's the variable that controls evaporation and discharge. So it will affect any hydrological model. You have to give you an answer, it must be, that's the first one I will take. Then later on I will take others like snow parameters, which is dominated by high altitudes, and routing is also very important at some point. But there is no limit, of course, in numbers. It's only computational power. But it runs even in a laptop, this model.
You're planning also to assess the effect on
if I plan to assess it,
well, you showed monthly discharge, the effect on the scale.
Yes.
Are you planning to do that also for topics or topic?
We have started a project in which we will try to analyze how it's affecting the extremes. I have some slides here, perhaps at the end. So we are doing, even with monthly values, that's the results in the US. For peaks, we are doing in uncalibrated conditions. We do relatively well. This is comparing to another model. And when we are in Germany, for example, for prediction of this very extreme discharge, which was in the Neckar in the 93, we were very close to the observations, and this is verification. So we are able to catch relatively well. Of course, in the time of the peak, no one knows the discharge, but we are now above the 100-year flat, and for a warning system, that probably is a good result. This kind of verification we will continue in the next months, and we are also trying to verify droughts, also extreme conditions on the other extreme. So we reconstruct, for example, soil moisture for Germany at daily basis, and based on that we estimate a soil moisture index. And here what you see is for example, for this development of the drought on 2003, how was the anomaly of the soil moisture with an ensemble of 200 members, and this is the percentage of area covered by drought in Germany in that time. So we are trying to assess at the moment in different places, at different scales, this how the model performs. And when we do that, perhaps later on we will introduce another model to check how the parameterization works in other kind of situations, other kind of physics. But I'm very confident. If it works in a simple model, it should work in a physically based model or more physically based model.